So we've talked about elements and compounds and mixtures, and now we're going to look at how we can represent them visually. And the way we're going to do that is with something called particle diagrams. Okay? We're going to use particle diagrams to visually represent the atoms and molecules of elements, compounds, and mixtures. So let's sort of, before we move any further with this, let's talk about first of all, what a particle is. So a particle is sort of a general term. It's a very small piece of matter. I also mentioned atoms and molecules. Now these terms are also going to be incredibly important. We're going to use them a lot this year, so let's make sure we know what they are. An atom is the smallest particle of an element that has the properties of that element. Okay? So it's the smallest particle of an element that has the properties of that element. A molecule, on the other hand, is two or more atoms that have been chemically combined. So you might start seeing a similarity to our definition of a compound there. Now let's take a look at how we can use these particle diagrams to represent some certain types of matter. First, let's look at how to make a particle diagram to represent the most basic form of matter, elements. The first thing I'm going to do is I'm going to start off by creating a key for my particles. So I'm going to use a red dot for oxygen. My first part of my key, the red dot, is going to represent atoms of oxygen. And I'm going to use a purple dot for iron. Okay, every purple dot is going to represent an atom of iron. So now let's come over to my actual diagram boxes here. In the box on the left, I'm going to represent iron. Iron is Fe as a chemical symbol. So, in my particle diagram, I want to represent what iron looks like, a sample of iron. So I'm going to pretend that this iron is a solid sample, because iron is very typically solid, and I've drawn in a regular geometric arrangement of the particles. So here's my particle diagram of iron. I've got all these atoms lined up nicely, and there's only atoms of iron present in the sample, so I can say that this is a substance. Okay? This sample, let's say the sample is only this big itself, has a uniform and fixed composition, and there's only one element present, Fe. So this is a particle diagram of an element. Let's go to the box on the right. Let's fill in oxygen. Oxygen is a gas, so it's going to be a little bit more spread out. And you'll notice that I am drawing pairs of atoms. Now you might stop and say, wait, aren't these chemically combined? Haven't I combined two or more atoms together? And you'd be right, I've combined two or more atoms together to make molecules. These are molecules of oxygen. However, this is still, and notice I represent that with an O2, there are two oxygens in every molecule. This is still a particle diagram of an element. As it turns out, oxygen is one of a few types of elements, a few kinds of elements that naturally exist in pairs. So we call these diatomic elements. And it's going to be useful to know what these are. I already said oxygen is one of them. Hydrogen is another. H2 is its normal sort of form. Nitrogen, we already said oxygen. Fluorine, okay, F2. Chlorine, Cl2. Bromine, Br2. And iodine. These elements all naturally come in pairs. They're diatomic elements. It's actually pretty easy to keep track of which ones these are. If we go look at our periodic table, you will see that the diatomic elements, here's hydrogen up in the corner, the rest of them form kind of an inverted L shape on the periodic table. Here they all are. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So we have this sort of inverted upside down L shape, or maybe it's a 7 if you want to look at it that way. But we have these 7 elements that are diatomics. Okay, so we just talked about elements. Now let's talk about how to represent compounds with particle diagrams. the same process again. I'm going to set up my key first. You always want to plan out the key that you're going to use so you can make sure you're representing things correctly. So let's stay consistent here. I will use red for my oxygen, and this time let's do hydrogen. I'm going to use a black dot for hydrogen. And I'm going to look at two compounds here, and we're going to talk about some differences between them. In the first box on the left, I'm going to have the compound H2O, water. And in the second box, I'm going to have something called hydrogen peroxide. Now you may be familiar with this. Hydrogen peroxide will bleach your hair, but it's also very reactive. It's used as a disinfectant and sometimes a propellant for rockets. So I've got two different substances here, water and hydrogen peroxide, and let's use a particle diagram to represent them. So in my water, I'm going to have a couple molecules here of water. Those are the oxygens, and they're going to have hydrogens chemically combined, chemically attached to them, little Mickey Mouses. Okay, so we have 3 molecules of water. You can see there's 2 H's, those are the 2 black dots, for every 1 red dot. Okay, and we have 2 H's and 1 single O in this formula for water. So you can start to get an idea of what a formula is used for, H2O. So this is water. Let's look at hydrogen peroxide, and then we'll talk about some similarities and differences. Hydrogen peroxide actually looks like this. We're going to put 2 oxygens together, and on each of these molecules there's also going to be 2 hydrogens. The formula for hydrogen peroxide is H2O2. So now let's sit back and take a look at this. What we actually have is water, a substance made up of hydrogen and oxygen on the left, and on the right we have a different substance that we just mentioned has very different properties, hydrogen peroxide, that has hydrogen and oxygen as well. So what's the difference between these two things? Well, the difference, hopefully that you've noticed, so the difference between water and hydrogen peroxide is that hydrogen peroxide has 2 oxygens and water only has 1. So they have different compositions from each other. So you can start to see how elements can actually not just combine in different combinations with each other, like different combinations of elements, but also in how many elements are put together in a single compound. So let's see what this particle diagram would look like if I cross out compounds here and we look at instead particle diagrams of mixtures. So to do this, I'm going to add in another element here. Let's use a blue color for, let's say, chlorine. Okay. Now chlorine is one of our diatomic elements. So let's put in chlorine into here. A couple of molecules of the element chlorine, Cl2. I've actually now made a mixture of Cl2 plus H2O in this one sample of matter. So this one sample of matter is representing a mixture of 2 different substances. And I could draw on a third one or a fourth one and make the mixture more complicated, but you get the idea. Now that we've looked at some examples of elements, compounds, and mixtures and representing them with particle diagrams, on your own I would like you to fill in through one example of each. So an example of an element, an example of a compound, and an example of a mixture. And make sure you use a key. So in your own notes, write out 3 of these blank boxes, and I'm going to pause the video now. You can go through and make up an example of an element, a compound, and a mixture. Okay, great. So that concludes classifying matter. We've talked about how we can take a very broad and general category like matter and break it down into substances or a mixture of substances. We've also talked about some distinctions within those categories, and we've looked at ways we can represent different forms of matter with particle diagrams. Whatever questions you have from this lesson, write them down in your notes and bring them in with you to class.